Hi, let's do an exercise, and let's see, we have this structure here with this, let's see, with this finishing lightweight board being, you see I don't see the dimensions. This value is given here, so that we don't need that, and we have this wood joist, which is this, and then we have a beam, it's like this. So the beam would be, you know, this beam would be these ones. So we have 3, and this one would be, you know, all these ones, right? You see what I mean? So just keep that in mind. And also we have so this. I think we ignored this. Okay. What we know, what we need to know, except from the numbers, is that we need to know the you know, the way, I don't know the correct word, but the more or less the weight or density of the D24 and C18. So for C18, the is equal to 4 kilonewtons per mm, and the D24 is equal to 6 kilonewtons per cubic meter. And also another thing we need to know is that single house family house, according to some code, it's you should add 2 kilonewtons per surface as the live load. That's used for calculation, and these are the only numbers we need for right now, at least. Okay, so let's continue. So with this in mind, we're gonna start with, so we're gonna calculate the load. There are more questions actually, but let's maybe expand on that later. So what we need to know is that, you know, we calculate, we start with this one, this joist, which being, you just take the area, so the height. Okay, let's write down that height times width times C18, which is you know, 0.2 times 0.1 times 4, which will give us 0.1 times 0.2 times 4, which is 0.08, and these are located, so we're going to take 1 meter, and these are how much that is per square meter. So there are, you see the distance between them are 40 centimeters. So that would, you know, we divide that by the distance to get per meter, right? So and that would equal 0.2 kilonewtons per square meter. So now we have that one, right? And now we'll take the other one. Oops, this one, you know. So we do exactly the same calculation. So 0.3 times 0.18, but this is a different kind of wood, right? So it's FD24, which I said before is 6, which will give us 0.3 times 0.18 times 6, 0.324. And also these are located every, as you see here, these are the beams, right? So this is located every 3.85. So 3.85, maybe we should do it separately so we don't increase. 0.324 divided by 3.85. 3.85 is giving us 0.08. Don't confuse that with that, by the way. So adding these two together would be the, you know, the weight of, and also we have this total weight of the other one. So it would be 0.08 plus 0.28, and that's a very, very small number apparently, and apparently it's also usually neglected. And let's continue. So what we want to do now is to okay, so the loading would be, so it would be this being dead load plus let's see. Oh yeah. Sorry, I forgot one detail that we're not gonna forget that, by the way. So total weight will be 1.5 plus 0.5, so that would be extra dead load. So here will be, so again, here will be the joist plus beam, and then we have 2, so that's 1.5 plus 0.5 equal 2 for the whatever that with a lightweight panel. Oops, that's not how it's called. Lightweight panel. And these are the dead weight, right? They're a constant self weight of the building. So so you'll do 2 plus 0.28 is equal to 2.28. This is the pure values. This is without safety factors. And also what I said before about single house, that's that's a live or leave load. Live or I don't know. It spells live, but they say leave. I have no idea. So that would be 2, right? And this would be, the G1, right? This no, maybe not. Okay, the G anyway. So this is the Q. The Q is for the live load. So the safety factor for Q is 1.5, and for G is 1.35. So with that, you can calculate the design load later, or now. Sorry. So you take this value, 2.20. Switch colors. 2.28 times 1.35 plus 2 times 1.5. So that would be, this would be 3. And the other one would be 2.28 times 1.35. 3 points. Never mind. Okay, so that's the wrong color, but 3.778. So that would be 6.078. Okay, so what we want to do now is that we have this. Let's see. So we have this, right? Zoom. Copy that. That's not the smooth way to do it, but okay. So so the load of that would be, we want to see how much load is on one of the beams. So that would be, would be like this. The whole of it would be like this, right? But it's going to be, placed like this, and it would be half on the ones on the side, and but otherwise it would be like this. So you take this part being one of a whole area. So what I said before, we 0.4. Yellow is a bad color to use. 0.4. So we just take this 0.4 times 7. We take this value instead, and that would be 0.4 times 6.08. That's 2.432. That would be throughout all the beams. So if you take this like this and like this as well, right? Then it would be, it wouldn't actually matter how stupid am I. So if we take the bending moments, the maximum bending moment, there would be the formula for something that looks like this, cubing 2.432. So let's see, I know this, but let's go and double check so I don't make a mistake. QL2 divided by 8. Right, this bad color. QL squared, so divided by 8 will give us 2.432 times 3.85 divided by 2 and cubed divided by 8. That would be 2.432 times 3.85 squared divided by 8 is equal to 4.5 kilonewtons per linear meter or per meter squared. I don't know. 4.5 in the middle. That'll be the same here. I just realized that's why I wasn't sure because that's irrelevant, So that's cool. 4.5. Okay, so same thing if we're gonna do with shear. I don't know if we can use that, but so we have Q being that, and the weight of this one, will be minus Q, the total length, L divided by 2, and this would be positive QL divided by 2, and that will give us 2.432 times 3.85 divided by 2. And that's 2.432 times 3.85 by 2. So that's equal to 4.68 and minus 4.68. And that would mean it would look like this. Minus half of it, like this. Minus 4.68 plus 4.68. Now I have I assume the VED, the sign value of, I don't know what the E stand for. But anyways, doesn't really matter, right? So now we have the diagram for that. So I made a mistake before. Actually, the values for, there was not actually F for this. It should be something else. It should be, I don't know what the fuck that. But because I got the real numbers later, so we need more actually later. But let's maybe I can write that down. So then also the FMD for C18 is equal to 8. This is also where I have this value thing given. The FMD D24 is equal to 11. Equal to 11. Equal to 11. Okay, so what we want to do now is to check that the maximum bending moment there due to self-weight, it's better than the material values that the joist the suffer will hold. So what you do is to find that we plastic for something is the base times height divided by. Okay, so what I wanted to do was to find what this actually is. I assume this is the maximum work of the elastic. I don't know, whatever. That's what I want to find out. So I used the right terminology, because again, remembering numbers and formulas is a bad way to understand something. But so this is a half-hard solution. Anyways, so the VEL elastic is equal to the base times the height squared divided by 6. So again, if you remember, we had the height were 20, the base was 10. So it would be 10, and also that's why the thicker the height width is the thickest, because it's better to have 2010 than the other way around. So 10 20 oops 6 gives us should probably be okay, so that would be let's see, 10 times 20 divided by 6 equal to 667 rounded, and with that we have to multiply that by the depending on the material. So for that's what we said before. So the FMD of C18, which is this one, the type of wood, right? Wood is 0. It's 8, and apparently you prefer it in some kilonewtons per square centimeters, and that would equal 0.8. So, and also the FMD for D24 is 11, so that will obviously mean 1.1. So it takes 6.67 times 0.8 to get the design value, and that would be equal to 5.533, and that's 5.33 kilonewtons. This is kilonewtons per centimeter, with being kilonewtons per meter. And so the here, 5.33 is higher than let's see the value we got here from before. So maximum, so here. So check that the MED is higher than the MRD. Sorry, like let's write it in the right way. MRD is higher or equal than MED. So again, MRD 5.33, the MED that we had before 5.5. So the maximum bending moment due to self weight, and the maximum in this one. So yes, it's okay. This is safe. And okay, so this is not done in the actual calculation, but I'm gonna do it just because to maybe understand something better. So if you remember, there was also this beam, right? Which was how big was it? It was 3018, right? So 3018. Again, as you see, it's higher. This is more effective, but this was for D24. If you remember, it was 1.1. So you take the base height, divided by 6 will give us 18 times 30 squared divided by 6 is equal to 18 times 30 by 6. 2,700 times 1.1 is equal to 2970. 29. Oh yeah, maybe because that's the smallest dimension. That makes sense. Because the other one was so much smaller, right? So, and also less hard, right? So that's probably why we don't need to check that, because and also that's a different part, but still, okay, let's continue. So we're gonna remove this layer, make a new. So next step would be to. Alright, next step is to do the deflection. And the deflection, the long-term deflection, DLT, is equal to the dead load plus 0.3, which could change depending on what type of building. 2, I think. Times Q. So GK plus 0.3 times Q is equal to DLT. So I assume that we use the so this would be the Q. This would be the no, sorry, that's not the Q. That's the QD. This is the QK. This is the GK. I don't know, small letter. So that would mean that the 2.28 plus 0.3 times 2 is equal to DLT. That would be, of course, that would be 2.88, right? But that doesn't say anything, right? So you take that divided by 11. I made a mistake again. This is not. I mean, that would be for a different thing, but what we want to do now is to do deflection, joist. And if you remember, there was something like this. This would be the joist. And then there's this beam. So the deflection would only take this one and these panels and stuff like that over. So that this would not be. So it would be less than what we do for the beam. Deflection joist. So what we said before. So we take 0.4 times 0.2. If you remember, that would be the. Because if you remember, we did like this. Then we take only this area, 0.4. Oops, that's the wrong color, but it doesn't matter. That would be that. So that would be the GQ. Sorry about that. Why is the GQ? Plus the Q will be 0.4 times 2, being 0.8. Actually, I think I made a mistake here as well. Let's see this. Yeah, so I'm retarded, obviously. This is incorrect. So the GK was what we said before. So we had the finishing material would be 2, plus the joist itself, which is 0.28. Equal, so that would be equal to 0.912. Just gonna double check so I actually understand. So this would be, this part would be, this part would be 2, and this would be 0.28. Is this correct? Yes, this is correct. Do you know, again, not to... The numbers coincide, that's why I had the confusion. So this would be 1b, because now it's just, that's what we did before, so it's 0.1 times 0.2 times 4, right? So that's 0.1 times 0.1 times 4. That's 0.08. Again, mistake. Ugh. So what? That's not a mistake. Okay, so now I actually understand the values again. So this GQ 0.91 plus 0.3 times 0.8. Being 0.3, again being the this y2, which is given depending on what type of building it is, and that would equal 0.91 plus 0.3 times 0.8 equal 1.15. So that's deflection long term. So with that, we have this calculation being the deflection of, so this would be the Q, right? Q. LT. I don't know, more or less the same, right? So that would be, formula for, so this would look like this. So Q would be 1.115, and this would be, I assume, 3.85 or 4. Which one is this? With the joist is 3.8. No, it shouldn't be like that. It should be times 2, no? Sorry, this should not be 2 because there's a joint between, so it doesn't matter. Even though the total is like that, it's still the deflection is, here and here, stops like that. So okay, so for Q here, the formula given in the sheet is the 5QL to the 4th divided by 384 EI. So so the EI for wood would be this is given also the for the C18 0.05 times the inertia. So EI C18, and the inertia, as we said before, it's we didn't say that before. Base height divided by 12, height to the cubed. So that would be, I would assume it would be 10 times 23 divided by 12, which would be 10 times 20 just divided by 12 is equal to 6667 per and so that times 0.05, so 6667 times 0.05 is equal to 333. So it would be, now we have this, so that would be this, so that would give us 5 times q, which is this, times 1.15 times this, 3.85 to the fourth power, 384 times 333. So it will be a huge number divided by a huge number. So we take that 5 times 1.15 times 3.85 to the fourth. That's divided by 3.84 times 63. So and that would equal 0.01. That's the absolute deflection. We don't care about absolute deflection, we care about the relative deflection. So 0.01 divided by 3.85. 3.85. You invert that. That would be 1 divided by 3. 9, which is less than 1.300, which is the thing. So that looks cool. So actually, now we have done everything with this, and the beam. That would be the. We'll do a different thing. So yeah, I assume this is have answered the question, except for the beam part, which I might do tomorrow, might not do tomorrow. Cool.